Chapter 3 is something I wouldn't actually introduce this early in the course if I were not trying to match the book that I selected. I think it makes more sense to talk about this along with metabolism, which isn't until late in the course, and so I will plant this in your mind, that when we start talking about glycolysis later in the semester, you might come back to this short lecture as a refresher. It is not uncommon to hear people say that life violates the laws of thermodynamics. One of the things that I hope is that by the time you are done with this chapter, you will understand that is not a true statement. The fact of the matter is that living organisms create and maintain their essential orderliness at the expense of their environment, and that the environment as a result becomes more disordered. The first law of thermodynamics is that energy can be neither created nor destroyed, but it can change forms. We will see that living organisms extract the energy stored in fatty acid bonds, glucose bonds, etc., and use that energy for a variety of things, including growth and development. The second law of thermodynamics is that the energy entropy of the universe is constantly increasing. Your book goes through, in an understandable fashion, these two laws, and I want to jump immediately to section 3.2, which is the concept of free energy. This concept was developed by Willard Gibbs, and we therefore refer to it as Gibbs free energy, which is that type of energy that can do work at constant temperature and pressure. And those last four words are crucial. Even a cold-blooded animal which does not maintain constant body temperature, the reactions occur at a constant temperature. There are a variety of equations relevant to the first and second laws of thermodynamics that your book goes through, and I'm going to skip. I'm going to jump to the equation that is moderately useful, which is delta G equals delta H minus T delta S. Delta H stands for enthalpy, and delta S stands for entropy, and thus this equation ties together both the first and second laws of thermodynamics. But this equation is still not completely useful in that it is difficult, though not impossible, to measure delta S. A more useful equation is delta G equals minus RT ln KEQ, because we learned previously how to deal with the equilibrium constant. And the other terms, R is a constant, T is whatever temperature the experiment is being performed at. It should be firmly fixed in your mind that when a delta G is negative, it is a spontaneous reaction, and the equilibrium constant must be greater than 1. And a positive delta G is a reaction that will not occur without the input of energy. And these will have an equilibrium constant less than 1. The 0 in this equation stands for standard state conditions. Which, as we previously talked about, is 298 Kelvin, which is 25 degrees Celsius, and 1 molar products and reactants, with the reaction carried out at 1 atmosphere. I did not bother to say anything about pressure before, since, as a practical matter, we carry out reactions in the laboratory regardless of what the atmospheric pressure is on a particular day. And as previously noted, and should become more clear now, biochemists need to use a modified standard state, which is to define the conditions as being pH 7. I should also note that your book uses the expression delta G 0 prime, which is the way I learned the expression. But a few years ago, it was determined by the nomenclature body that we should be using delta G prime 0. I will try to remember to always do that, although I do slip up sometimes, especially when I'm being distracted by the book doing it wrong. The really, really important thing about delta G values is that they are additive. As shown in the reactions on this slide, glucose does not become phosphorylated in the presence of phosphate because it has a positive delta G prime 0 value. And ATP spontaneously decomposes when placed into water because it has a large negative delta G prime 0. Mother Nature, in her infinite wisdom, has found that enzymes can couple these two reactions together such that when glucose and ATP are mixed together in the presence of glucokinase, the enzyme causes the glucose to be phosphorylated to glucose 6-phosphate as the ATP is hydrolyzed to ADP. Notice that the delta G of these two coupled reactions is the sum of the individual reactions. An extension of this is that the delta G depends on the actual concentrations. Remember that delta G0 is the reaction when we are mixing together 1 molar products and reactants. But physiologically, our glucose level is maintained at 5 millimolar and therefore will proceed at a different rate than at 1 molar. This slide gives the equation to use in examining this phenomenon, and you should commit this equation to memory. As an example problem that you can look at in working through problems in the book and homework, and plugging in these numbers, one of the things that I should note is that I'm using 310 kelvins here, which is not the standard state. Rather, this represents the body temperature of humans of 37 degrees. If we do this calculation using actual values determined in the laboratory of DK Srivastava, which is data that we'll put in the announcements this module, it will change the calculation somewhat. Notice, though, that the delta G value is similar to the delta G0 value. Both are around 10 to 15 kilojoules per mole, and both are negative values. In biochemistry, it would be very unusual for a delta G value to switch from positive to negative or vice versa. Another thing about these delta G values is that they are influenced by enzyme coupling. In other words, if glucokinase, which is the enzyme that catalyzes this coupled reaction, interacts with phosphoglucoisomerase, which is the next enzyme of the pathway, and does a handoff, then the concentration of product of enzyme 1 will be essentially 0, as enzyme 2 immediately converts it to some other molecule. This leads us to a concept called phosphorylation potential. Using the above methods, it is possible to determine whether ADP or AMP or other molecules can cause the phosphorylation of glucose. I would encourage you to do these calculations to test your understanding of this concept. Do the calculations with ADP and AMP and the phosphorylation potentials on this slide. You should be able to note without doing calculations that the delta G value for ADP is approximately the same magnitude as the delta G for ATP. In fact, it's the same number. But that AMP has a delta G only about half as large. Chemical reactions are driven by both chemical and electrochemical means. Similar to the equation to use in calculations involving reducing agents is either delta G equals minus NF delta E, or delta G prime 0 equals minus NF delta E prime 0. F is the Faraday constant, which you shouldn't memorize, but know where to look it up. But it's 96.5 kilojoules per volt mole. Similar to phosphorylation potential is reducing potential. A table of a small number of standard reducing potentials is given on this slide to use, and I intend to assign a problem using reducing potential. Several tables of values, in addition to those given to you in your book, will be loaded into the announcements section of the class when this problem set is assigned. Keep in mind that delta E values can be added together just as delta G values by the coupling of reactions.